Hello all, welcome to the presentation. My name is Saranya and I've been working as a verification engineer at Analog Devices Bangalore for the last 4 years. The topic of the session is analog modeling to suit emulation for hardware-software co-verification. So let's dive in. First, to the background. Firmware or boot code is the program that is burnt into the ROM, that is the read-only memory of the SoC or system on chip. It boots up and configures the SoC. In the process of SoC development, firmware is developed in parallel to digital analog design by referring to the specification. Now, any bug in the firmware code will be difficult to debug in silicon, which will delay the delivery of silicon to the customers. It may also result in a silicon respin. Verifying firmware routines pre-silicon is necessary, but the regular RTL simulation environment is very time-consuming as it can go on for days. This is where emulation comes into the picture, where firmware verification tests are run on it. These tests can run from seconds to minutes depending on the size and the code of the duty. Bringing up the duty for emulation is not straightforward and has its own challenges. It requires modeling of some blocks, especially analog, to make the design of the test, that is the duty, synthesizable and suit emulation. The biggest challenge was to make the analog components modeled as real number models in simulation portable. Typical modeling flow is shown where the analog circuits or real number models are converted to synthesizable models. As an example, some logic of the modeling done for an ADC block, which takes an analog input and gives a digital output, is shown. Data types such as float and real are non-synthesizable constructs. This was solved using fixed point arithmetic. For example, here we have real numbers. Now in fixed point, we multiply the real number by a scaling factor such that we can represent it using integers. But this has the cost of losing resolution in the decimal points. For example, here the value of a is 0.0025. To represent it as a fixed point number, you scale it by a factor of 2 power 10. Rounding it off gives a value of 2, and in the process, resolution error is 22%. The same number when scaled by a factor of 2 power 20 gives a much lesser resolution error, that is, it's only 0.4%. Thus, greater the scaling factor, lesser is the error in resolution. But larger scaling factor implies higher bus width, for which more ports need to be punched into the design. This wider bus arithmetic would slow down the emulation platform too. The above calculation was incorporated into a Python code and a plot of the error versus bit width was developed, as shown on the left hand side. The right plot shows a visualization where error is plotted for different bit widths. It shows how the error in resolution decreases with increase in bit width, but eventually saturates beyond a point. For our project, we chose 14 as the bit width. Next, scaling and trimming was done internally to save the number of input-output pins. Inside the module, there may be real number multiplication. For example, consider the following multiplication of two numbers, 120 denoted as A and 0.000392 denoted as B, where B is the least significant bit of an ADC. Now you scale A with the power of 2 power 14, with a factor of 2 power 14 and round it off. You scale B with 2 power 14 and round it off. And finally perform the math to get the error after multiplication. Assuming ADC LSB is 0.000392, we compare the error with respect to LSB. That is, how many LSBs is the error. Next, we scale the multiplication with a factor of 28, and that gives much lesser error. That's about 1 LSB. These approaches were adopted for modeling of analog blocks in our project. This table shows the comparison between RTL simulation and emulation time. All the tests were run before the silicon came, and this saved time in the crucial window between silicon arrival and sampling to customers. For example, chip initialization routine, which took 2.5 days to run on RTL, took only 40 minutes on emulator. Apart from this, several firmware bugs were found pre-silicon. These issues, if found post-silicon, would have definitely delayed the time to market. So we've come to the end of the talk. Some key takeaways for the audience are to accelerate pre-silicon firmware verification, emulation is the way to go. And to achieve its benefits, synthesizability and analog modeling must be kept in mind. This presentation shows how fixed point modeling can be used to effectively model analog components. I would like to extend my gratitude to my leads and colleagues of the Autonomous Safety Group at Analog Devices and for their constant encouragement and support. Thank you.